Hi, this is Somaiah, working as assistant professor in the Department of Mechanical Engineering. Welcome back to the course of Fluid Mechanics and Hydraulic Machinery. So today I'm going to discuss about the working principle of a Francis turbine and various components of a Francis turbine. According to the classification, the classifications of a Francis turbine under which it falls, and so what is the importance of a importance and applications of a Francis turbine? So according to the available energy at the inlet of a turbine, the turbines can be classified into impulse and reaction turbine. So under impulse turbine, so the inlet energy, the energy available at the inlet before entering into the turbine rotor runner, so the kinetic only kinetic energy will be available. So in that only Pelton wheel turbine, John wall turbine will comes under, and we have gone through the Pelton wheel turbine. Similarly, according to the available energy at the inlet to the runner, so the reaction turbine will be based on if the kinetic energy and pressure energy is available. If both these energies are available at the inlet of a runner, then such type of turbine is known as reaction turbine. So in this reaction turbine, before entering into the turbine, the pressure will be high and kinetic energy will be small. The substantial energy will be remained as a pressure energy, but only the partial energy will be remained as a kinetic energy. But after working on a rotor, the pressure energy will be reduced and kinetic energy will be increased. So, but with this kinetic energy, increased kinetic energy and reduced pressure energy, the water can't be taken out from the exit of a rotor. So, in order to in order to convey the water from the exit of a turbine to the tail race, there is a necessity of drop tube in these reaction turbines. But in case of impulse turbine, there is no necessity of drop tube. But in case of reaction turbine, that is required. And the difference between the pressure available at the inlet of a runner and to the available pressure and at the outlet, the pressure difference between the inlet to the runner and outlet of the runner is known as reaction. So the reaction turbine is based on complete the pressure difference. In order to have the pressure difference, the complete the turbine should be enclosed in a watertight casing. In a watertight casing, it is to be submerged, so that there will be pressure difference between inlet and outlet of a runner. And due to this pressure difference and the turbine starts rotating. So when the working coming to the force through by which it is generated. So there are two forces here. One is force due to kinetic energy. Another one is force due to pressure energy. So but in case of impulse turbine, only the force is generated due to kinetic energy. But in case of reaction turbine, the force can be the summation of due to both kinetic and pressure energy. So with this energy, the water strikes on the rotor blades. So due to that, they starts rotating. Whenever it is rotating, there will be it is connected to a shaft, and the shaft is connected to a generator. Thereby the power generation will be taking place. So in this category, in a reaction turbine, so there will be again there are two types of turbines based on the type of flow. According to the flow direction, it can be again classified as per the present the syllabus through which we are going. There will be one is Francis turbine, another one is Kaplan turbine. So both are reaction turbines only, but based on the type of flow which is which is found in a particular turbine. If it is in case of Francis turbine, the type of flow is mixed flow turbine. It is mixed flow we can we can find here. So that is due to radial and axial flow. Both will be available, radial and both so axial. It enters into the rotor in radial direction and leaves axially. So therefore this comes under a mixed flow turbine. But reaction only, there will be a pressure difference between inlet and outlet of the water which is flowing over a turbine. And similarly, Kaplan turbine. In Kaplan turbine, the direction of water flow is only axial. Therefore, this axial flow reaction turbine and Francis turbine is a mixed flow reaction turbine. But these two are reaction turbines only. The reaction turbine is one which utilizes the pressure difference of a liquid water which is passing over a turbine between inlet and outlet. So that is nothing but a reaction. But under reaction, so based on type of flow, there are different types of turbines. Based on type of flow in the turbine, it can be classified, even though it is reaction turbine. So in reaction turbine, there will be Francis turbine, Kaplan turbine, propeller turbine, etc. The Francis turbine is a mixed type of reaction turbine. So as we have discussed now, it is comprised of in reaction turbine, but mixed flow. There will be axial and radial flow. The entry will be radial onto the blades of your turbine, and while leaving, so the flow direction will be axial. Means it is parallel to the direction of rotation of a shaft. So therefore, there will be two available flows. That's why it's known as a mixed flow reaction turbine, and it is named after James B. Francis, who was first to develop inward radial flow type of reaction turbine. Later on, it was modified, and modern Francis is a mixed flow type of turbine in which water enters at the periphery of a runner and leaves axially at the center. So that's why it's a mixed flow reaction turbine. So is named after Francis, who invented first the inward radial flow turbine. Afterwards, so that is converted into radial and both axial flow. It is utilizing both the flows. The performance and efficiency of the turbine is dependent on the design of the runner blades. So the runner blades are designed in such a way that it has to extract the maximum energy from the water, and so that the maximum power generation will be there. So therefore the blades are designed in such a way that to utilize the complete maximum possible energy possessed by the water. Here the blades are designed in such a way that in order to extract the energy due to kinetic energy. So one is the force is developed due to the kinetic energy, and another force is generated due to the pressure energy. So these two energies are available, and due to that the force generated is greater than to the force available in a Pelton wheel turbine. In case of impulse turbine only, the pressure, the kinetic energy is available. The entire energy of a liquid converted into only kinetic energy, where the force due to kinetic energy is developed. But in this case, there are two types of forces are available. In a Francis turbine, runner blades are divided into two parts. The lower half is made in the shape of a small bucket, so that it uses the impulsive action of water to rotate the turbine. The upper part of the blade is use the reaction force of water flowing through it. So there are in two parts. The blade is divided into two parts in order to extract the one is the force due to the reaction, another is force due to the kinetic energy. So that is nothing but the force. The reaction force is due to the difference of pressure. So one is pressure energy, force due to pressure energy, another one is kinetic energy. Thus runner blades make use of both pressure energy and kinetic energy of water and rotates the runner in most efficient way. So in this diagram we can see the skeleton, the different arrangement of different components of a Francis turbine. So here in Francis turbine, it is a water, as we discussed, the turbine will be enclosed in a watertight casing. So this is actually a rotor on which blades are arranged in such a way that to extract the force due to kinetic energy, also due to pressure energy. So the blade is made into two parts. So the upper half will be extracting the force due to kinetic energy. So in this diagram, the position of a shaft is vertical. Therefore, the rotation of a turbine will be in the horizontal direction. In vertical direction, there is a shaft, and it is completely enclosed in a watertight casing. So that is nothing but a scroll casing. Here in this scroll casing, it is filled with a water. So in this scroll casing, here we can observe the varying diameter of a scroll casing. Here the diameter is smaller if you compare with this portion. So this is in order to maintain both the energies. So as the diameter of a scroll casing is decreasing, the pressure energy will be decreasing, and kinetic energy will be gradually increasing. But before entry into the at the entry of inlet to the rotor blades. So therefore, the scroll casing is not uniform diameter. It must be gradually decreasing diameter, so that it will possess both kinds of energies. So another one is there is a vertical shaft. It is connected to a rotor. So the steerings will be there in between. The blades are connected, and before water coming into the directly onto the blades, onto the runner blades, there will be stay vanes. They have to pass through stay vanes. So first is this is a stay vane, and this is fixed in between steering. So before that, the guide vane will be there. So after that, then the water will be entering into the turbine runner. So because if there is no guide vane, here we can see guide vane, and after that there will be steering, and there will be stay vanes. So after that, there will be inside turbine runner blades will be there. So without guide vane and stay vane, so the efficiency of a Francis turbine is not high. So because the guide vane guides the water, and in order to arrest the input jerks of the water, sudden increase in pressure, or if there is any disturbance from the incoming water, that will be extracted by steerings, and the particular amount of liquid and in the angle of attack will be controlled by guide vanes and stay vanes. Therefore, without these guide vanes and stay vanes, the flow of water and also the performance of a turbine is not high. So after that, after working on a turbine, there will be a draft tube. Through this draft tube, the purpose of a draft tube is to convey the water, to carry the water from the exit of a rotor and to the tail race. So because the tail race will be at atmospheric pressure, pressure is atmospheric pressure here, but at the exit of rotor, after working on a turbine, the pressure will be decreased. Here vacuum pressure will be there. There will be negative pressure, the pressure less than to the atmospheric pressure, and here vacuum will be. With that vacuum pressure, the water cannot flow into the high pressure zone into the tail race. So in order to pass this water from this exit to here, the draft tube cross section is gradually increasing. So due to that, the kinetic energy will be decreased, the velocity will be decreased, and pressure will be increased again. So with that increased pressure, the water will be submitted into the tail race. That is the purpose of a draft tube. So in this diagram, we can see how the flow is taking place, the direction of flow. So as this is the inlet, the water is flowing in this direction, and then after passing through the stay vanes and guide vanes, it enters into the turbine vanes. So this is a first of all is passing through stay vanes, then guide vanes. Afterwards, in is gradually, as this is scroll casing, it is gradually decreasing. So by having these two kinds of energies, the water will be entering into the guide vanes and stay vanes. After that, turbine, after working on that, then there will be draft tube again. It enters into the tail race. In this diagram, this is a sectional front view. Here we can see again the Pelton wheel with a smaller diameter. If you compare with this diameter, that means the scroll casing is a gradually decreasing cross sectional area. The water will be flowing in the circular direction. Then after passing through that, then there will be a guide vane, stay vane. After that, it enters a runner vane. The water coming is in this direction, and after working on that, so it will be leaving in this in the axial direction. So therefore, it's a mixed flow type of turbine. Say sectional top view. Here we can see the arrangement of different types of vanes. So first of all, the water enters from a penstock into the scroll casing. The scroll casing, as it is gradually decreasing cross-sectional area, so it will be maintaining two kinds of energy. After that, it enters into a stay vane, and this is a steering. So the stay vanes are fixed in between the steering. So these two ends will be fixed in the stay rings. So the stay rings will be half of the number of guide vanes. The guide blades will be equal to the double of almost the turbine runner vanes. So after water is moving through passing through the stay vanes, then it enters the guide vanes. So guide vanes will be guiding the water onto the turbine, the rotor vanes. So where the angle of attack will be controlled. The guide vane mechanism, the stay vane mechanism will be controlled directly with the help of a governing mechanism. So with the help of governing mechanism, the amount of water required by the turbine can be varied. So in power plants, automatically based on the demand of a power from outside, it will be regulated automatically. So the angle between the guide vanes will be closed or opened based on the requirement only. It will be automatically. The mechanism is connected to a governing mechanism, so that angle between these two blades will be controlled. The stay vanes can be fixed at a different particular angle in such a way that the the maximum amount of liquid is allowed, and so that the angle it can be varied whenever it is required, manually or automatically. So after that, whenever it enters onto the turbine runner, the turbine runner will be gradually moving due to these forces of a water, and as it is connected to a shaft, the shaft will be rotating. So but based on the head available before hitting the turbine of a Francis turbine is a medium flow turbine. Therefore, this will be under 60 meter to 250 meter. There will be head from a reservoir level to turbine center. The scroll casing, different components of the Francis turbine. So as we discussed, we have seen in the previous diagram how they were located at different places, and the functions of the Francis turbine is the water from the penstock enters the scroll casing or spiral casing, completely surrounds the runner. The purpose of casing is to provide even distribution of water around the circumference of the runner, and to maintain constant velocity of water so distributed. In order to maintain a constant velocity of water throughout its path around the runner, the cross-sectional area of the casing is gradually decreased. The casing is made of cast steel or plate steel. Steering. So here the purpose of steering is, there are two functions. One is to direct the water from scroll casing and the load imposed upon it. Another one is the load imposed upon it, the internal pressure of water and the weight of the turbine and electrical generator and transformer is the same to the foundation. So the inlet water jerks coming from the water, so will be bearing by the stay vanes and will be will be transferred to the foundation. The guide vanes from the steering, the water passes through a series of guide vanes provided around the periphery of the runner. The function of the guide vane is to regulate the quantity of water as supplied to the runner and to direct onto the runner blades with a designed angle. The angle of attack of water will be designed decided by the guide vane. So therefore, the guide vane angle is directly connected with a governing mechanism. As the angle between the guide vanes are reducing, therefore the amount of water supplied to the turbine will be reduced when there is no requirement of a power from outside. If there is high requirement, the guide vane mechanism, as it is connected to a governor, it will be opened automatically, the angle between the guide vanes. So by a system of levers and links, all the guide vanes may be turned about their stems so as to alter the width of the passage between adjacent guide vanes. thereby allowing variable quantity of flow according to the requirement from outside. The guide vanes are operated either by means of a wheel or automatically by a governor. Runner. The runner of a Francis turbine consists of a series of curved vanes. The number of vanes on a runner will be 16 to 24, evenly arranged above, around the circumference in the annular space between two plates. The vanes are so shaped that water enters the runner radially at outer periphery and leaves it axially. Therefore, it is a mixed flow reaction turbine. So the change in the direction of flow water from radial to axial as it passes through a runner produces a circumferential force to the runner, which makes the runner to rotate and thus contributes the useful output of the runner. So there will be conversion in a water, and during conversion there will be a development of circumferential force on a blade. So runner vanes are made of SS, and other parts are made of cast iron or cast steel. The runner is key to shaft, which is usually forged steel. The torque produced by the runner is transmitted to the generator through a shaft, which is usually connected to the generator shaft by a bolted flange connection. So here we can see the working principle of a how the water enters and how it is passing through the scroll casing, and afterwards stay vanes, then afterwards guide vanes, and then on to the turbine vanes, rotor vanes. After that, how it is entering into this draft tube, how it is leaving. The flow of water over a different parts in this diagram, in this video, we can observe.
Francis turbines are the most preferred hydraulic turbine. It contributes about 60% of the global hydropower capacity, mainly because it can work efficiently under a wide range of operating conditions. Most important part of Francis turbine is its runner. It is fitted with a collection of complex shaped blades. In runner, water is entered radially and leaves axially. During the course of flow, water glides over runner blades. Francis turbine blades are specially shaped. You can note that blades are having thin airfoil cross section, so when water flows over it, a low pressure will be produced on one side and high pressure on the other side. This will result in a lift force. You can also note one more peculiar thing about the blade. It is having a bucket kind of shape towards the outlet. So water will hit and produce an impulse force before leaving the runner. Both impulse force and lift force will make the runner rotate.
There will be two kinds of forces. One is impulse force, another one is a lift force.
A portion of force comes from impulse action.
The total force is nothing but the reaction force plus impulse force. As it is, there are two kinds of energies are available. One is kinetic energy, another one is pressure energy.
They are also called mixed flow turbines. The rotor is connected to generator via a shaft for electricity production. This arrangement is fitted inside a spiral casing. Flow is entered via an inlet nozzle.
See, while input is coming from penstock and enters into a scroll casing, after that how it is swirling around the periphery of a rotor vane.
But decreasing area of spiral casing will make sure that flow is entered to runner region almost at uniform velocity. Stay vanes and guide vanes are fitted at entrance of runner. The basic purpose of them is to convert one part of pressure energy to kinetic energy. Flow which is coming from the casing meets stay vanes. They are fixed.
So this is a real turbine where we can see the installation of a Francis turbine in real situation. This is taken from this is rated at nearly 1 million HP or 750 megawatts, being installed at the Grand Coulee Dam, United States. So here we can see the Francis turbine, the blades and its design, how it is going to be installed in such a huge installations for the development of huge power, 750 megawatts. Here we can see the velocity triangles of a Francis turbine where runner vane. As the Francis turbine runner vane is backward curved vane, here we can, as the water is coming in this direction, therefore here we will have two kinds of velocity triangles. But in case of Pelton wheel turbine, so as it is tangential flow, we have inlet velocity triangle is a straight line, and outlet velocity triangle is having of four different lines. But here we will have inlet, one is inlet triangle, and another one is outlet triangle. So this is a rotor in between between the two plates. The runner blades are mounted, and is the center of that rotor. So here we can see as the water is passing here, this will be absolute velocity of a inlet jet, and due to that u1 will be there, blade will be moving with particular velocity, that is blade velocity, and between these two there will be relative velocity vr1, and if that v1 inlet jet velocity is will be divided. If you split this inclined line, this jet velocity into two components. If you resolve this line into two components, one is the horizontal component or the vertical component. This vertical line is known as Vf1, and horizontal line is known as while velocity, Vw1, Vf1, and we got V1, Vr1, and U1. So we have already we have discussed these velocity components in previous classes, and alpha is a inlet jet angle, and theta is a inlet blade angle. Similarly, various parameters at outlet velocity triangle also, but V2 after flowing over a inner surface of a blade, the velocity will be decreased, therefore V2 will be here. And from V2 you can resolve this V2 into two components. We have Vw2 and Vf2. The horizontal component is while velocity, and as there is a movement in a blade, due to the V2 there will be U2. So between these two there is a relative velocity Vr2, and similarly phi beta. So phi is a outlet blade angle, and beta is a outlet jet angle. So these are the various velocity components on inlet and outlet velocity triangle of a Francis turbine. In order to determine the work done, we should know the velocity triangles of a Francis turbine. So work done, now we know that is force into distance, the force about x direction into u. So we have derived in the previous classes, the force is rho a v1 into Vw1 plus Vw2 when beta is less than 90. When beta is less than 90 in outlet velocity triangle, there will be plus. If it is greater than 90, minus. So that's why it is written as plus or minus. So Vw1 rho a v1 into Vw1 plus Vw2 is a force along x direction Fx into u. So we have two different velocity, blade velocity at inlet and outlet. Therefore, so Vw1 into u1, Vw2 into u2. So this is nothing but this is the expression is for work done. Work done by the jet on runner per second. So this can be written as rho a v1. Rho a v1 is the AV1 this is equals to volume Q. Q is a discharge or rate of flow, area into velocity. So therefore it can be substituted with Q, rho into Q, Vw1 U1 plus or minus Vw2 U2. This is the work done on a Francis turbine. So U1 is the tangential velocity of wheel at inlet. This can be calculated by using 5d1 n by 60. From this equation, we can calculate inlet blade velocity or runner inlet diameter and speed of the turbine also. Similarly, U2 equals to 5d2 n by 60, where d2 is inner die of runner, where d1 is outer die of runner. N is speed of the turbine in RPM. Work done for second for unit weight of water striking for second. The unit weight is specific weight into volume. So this is specific weight into volume. Here we can see rho Q VW1 U1 plus or minus VW2 U2. This is the work done we have derived in the previous slide. This is equals to a specific weight into a volume. So where specific weight is weight for volume, weight is specific weight into volume. So therefore, we'll get 1 by G as rho and Q can be cancelled. Rho Q can be cancelled. 1 by G into VW1 U1 plus or minus VW2 U2 Newton meter per Newton. So this is work done per second for unit weight. As the angle beta is an acute angle, there will be positive sign. Otherwise, if the beta is greater than 90, obtuse angle, then negative sign will be taken. Or if it is beta equals to 90 degrees, then VW2 becomes 0. In this case, VW2 is 0 whenever beta is becoming 90 degrees. So whenever beta less than 90 or greater than 90, there will be VW2 component. But when beta becomes 90, there will be no while velocity at outlet velocity triangle. So in that case, the work done for unit weight for second is 1 by G into VW1 U1 because VW2 becomes cancelled. In this case, VW2 U2 will be cancelled. Hydraulic efficiency of a jet. So that is the ratio of output and input. The work done by the water on a the turbine blade is rho Q VW1 U1 plus or minus VW2 U2. This we have seen. But the inlet energy of a water is rho G QH, less water energy. Therefore, we'll have after the cancelling the rho Q, VW1 U1 plus or minus VW2 U2 into GH. This is the hydraulic efficiency of a Francis turbine. If the discharge is radial at outlet, then VW2 becomes 0. Therefore, hydraulic efficiency also, in that hydraulic efficiency, we have to remove this VW2 U2 component as it is becoming 0. Degree of reaction. It is defined as the ratio of pressure energy change inside a runner to the total energy change inside a runner. So the difference between these two, the ratio of pressure energy change inside a runner to the total energy change, pressure energy change to total energy change inside of runner is known as degree of reaction, denoted by R. This will be calculated in coming the problem solving classes. The speed ratio, some other empirical relations are there for Francis turbine in order to calculate the problems and to determine different unknown parameters. We have to come across of some relations. The speed ratio can be given as Ku equals to U1 root 2GH. We have seen already U equals to Ku root 2GH. Similarly, V equals to CV root 2GH. So this is a jet velocity and this is a blade velocity. From this Ku into root 2GH or Ku equals to U by root 2GH. So flow ratio is denoted by psi. Psi equals to Vf1 by root 2GH or Vf1 equals to psi into root 2GH. So discharge of the turbine can be calculated by using this equation. Q equals to pi d1 b1 Vf1. So where d is diameter, d1 is outer diameter of a runner. Similarly, width at exit, width at outlet of runner is b1, and similarly flow velocity at outlet say Vf1 or Vf2 is outlet, then V1, Vf1, B1, D1 will becomes inlet of the runner. Runner diameter at inlet, D2 becomes outer diameter of runner. Similarly, B2 also, width at outlet, width at inlet. The head on turbine will be given as Ph equals to P1 by rho g plus V1 square by 2g. So the combination of the pressure energy and kinetic energy, they are converted into meters of water. The ratio of width wheel to its diameter is given as n equals to b1 by d1, varies from 0.1 to 0.4. These are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.